Okay, so now I think we're recording. Okay, good. Yeah, I'm sorry. So that was my fault. I should have written 12:15 to 2 o'clock. So the lecture is 1 hour, and then we will switch to next week. So that's the first message, and I'm sorry about the confusion. I have too much to do. It's only my fault, and you shouldn't suffer. Um, and the second one is that project 2 is posted. I said that yesterday, so please get going on project 2. And the last message is that project 1 should now be corrected. And I don't know if you got an email from Javier and me this morning. So Javier was supposed to send this out. I didn't check my mail. I don't think he sent it yet, but he will send an email to each one of you as a group where you get a score, and you also get some kind of corrections that Javier and myself did. So I hope this is some valuable feedback to you in how to sort of write a report. And most of the reports were really good. So I'm impressed by your work, and thank you for working on this in this difficult time. So then if there's some more questions you have based on our feedback, then you can contact us in class or via email. And then for next week, we will finish off the topics on the exercise session today is digital. So still digital. But for next week, we will have both, and also for the week after, we will have both. So then we'll, and also for the lecture sessions in the last week, we will have both digital and physical. Unless something happens today. I heard there was an announcement today, but I would be surprised if something happens in Trondheim. Okay, so then next week we will then round off this experimental design with some fractional experiments and blocking of experiments, and also cover briefly response surface methods. And then after that, it's project 2, and then it's Easter break. All right, so we were talking about factorial experiments in this setting where we had factors at high and low level. And then there's one mean value that we get out of this, and k main effects that represents the variability of factor A around high and low for this one. And then factor B also, how it varies around the mean when it's high and low, just B, high and low, not caring about the others. And then there's a bunch of interaction effects. So these first order interactions are AB, AC, BC, when two factors work together. So they can be also high and low, and we can study when they are jointly high or jointly low, how that influences the response. So altogether, there's a bunch of effects here, and in some settings we might ignore these very high order effects and instead use them to estimate the variability. So that was where we ended yesterday and where I will continue today before we go into analysis of variance discussions. That's the topic for this lecture. So if we have 2 to the power k data and we have 2 to the power k variables because we have mean, main effects, interactions, and higher order interactions. So then we have just as many data as variables we could be interested in. So there's a problem there. We don't have any kind of redundancy to estimate the variability. And what we discussed yesterday was either to specify this sigma squared from replicate measurement. So that means you're observing many y for different for the same configuration of high-low levels. Another one is to estimate the effect directly in by saying that higher order interactions are basically just random variation around zero. So these are two different methods, and there's also a third one called lengths method that we will just go through very briefly. Okay, so then we said, okay, so these effects that we have here, they are random variables. So what is an effect hat here? It's a linear combination of some ci, yi. So we find linear combinations. So if it's the mean, all these ci are 1. If it's a first order effect, we have ones and -1 where we take the response at high and low level. So because this is a linear combination of 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 data y, and the y's are considered to be Gaussian, then we can calculate the expected value of this and the variance of this, and we know that the effect should be Gaussian distributed. And the sigma square effect would then be the sum of all these c's squared, and then the variance of this sigma squared, or sigma squared and then times the ci1. And then we take the average at the high and low level. So this ci is then 2 to the power k minus 2. So we see that sigma and sigma effect, they are connected in some way. So then the estimation using higher order effects is then simply to go directly on this, not caring so much about this. And then we estimate this by taking the sample variance of the higher order effects. And since we estimate sigma, we get a t distribution, and we can reject if this one is higher than the percentile. So this is t alpha nu, and then this is minus. So this would be the rejection region. That's what we discussed yesterday. And I didn't have so much time to go through examples. So now I want to have this example with some experiment where there's a catalyst here that can be on and off. And then there's a temperature variable that can be high and low, pressure variable high and low, and the concentration level at high and low. And in this process, you study its development and measure the effect you get out of this. How well is this going? And we can then go through the usual calculations at high and low level, taking the difference of data when A is at the high level and A is at the low level. And then we get this effect for the catalyst. And there are two effects. So we see that there's one effect called the coefficient, and the other is called the effect. And that this is half of the other. So this would be the A effect, and this would be like the B effect, where they are connected. So it's either the regression view or it's the high and low level view. Yeah, so in this case, the effect goes from 1 to 100. You measure the what's this called? I think it's virkningsgrad through some process. I don't know what that is in English. So you can how much do you get out, how much energy do you get out of a production process? It's either nothing, then everything is lost, or you try to get all energy through the system. So then you would see that some of these effects are large, like temperature stand out as very large, but some of the others are much smaller. Efficiency is the name for this effect. So we can then go through this exercise and study the big effects. And in this one, we can compute variance estimates by setting the higher order equal to 0. So we basically say that ABC is equal to 0, and the same holds for ABD equal to 0, and all the way down to ABCD, which is equal to 0. So this is our assumption that the true effects are 0. True effects are 0. So not all effects, but these very higher order effects. Of course, A, B, C hat is the usual linear combination of data. So this will not be 0. But we say that the true is 0. So then this will just represent random variation around 0. And since it's random variation, it should be representative of our sigma squared noise term. And this, again, is transformed into the sigma squared of the effect, as we saw previously. And they are related. Okay, so then let me show you this in Minitab, how it works. So here's Minitab. Yeah, so this is not the right example. This is the right example where we see this efficiency. And then we can go here and compute DOE, design of experiments, factorial, analyze, factorial design. And we put in this effect and we say how many terms we want. And if we include all 4 terms, we don't get anything left for the variance estimations. So I will say that we only want the first 2 terms. So that means we get A, B, C, D, and then AB, AC, AD, and so on up to CD. And that's what's the selected terms here, which comes out automatically. So then we get the results, and we see that there's a SE coefficient here estimated from the variability of these higher order terms. And the actual effects are exactly the same as we had in this printout, even though I computed this from the case with all effects was in there. The calculation there is exactly the same. The only difference is that we get an estimate of the variance because we removed the higher order interactions. Yeah, and this can also be interpreted as a regression line where we then take in our regression model, we have the mean and then an effect of catalyst on and off. So here we can plug in catalyst -1 if it's off, or 1 if it's on, or vice versa. And then temperature high and low, pressure high and low, and then we see this interaction effect where we multiply these effects or inputs. Yeah, and then we see this plot, and you might see a difference. Now this is the plot I have here in the printout. So the temperature and the catalyst and the concentration appear significant, and also an interaction between temperature and concentration. and maybe also C, but not so much. So the other ones are P relatively small. Of course, we could go one step further here and say that we're only interested in the main effects and don't care about interactions at all. That is not so common. But then we say that we only want the first term, and then we use all the rest to estimate the variability. And then we get the same effects, but we get a new SE coefficient because now in this estimation of sigma effect, we also use the second order the first order interactions. So that means AB, AC, and so on. So they are not included here. We see only the main effects, and they're all significant except maybe pressure, which has a relatively large p-value. Okay, now you see this value changed here and how it's computed. Okay, so there's another way of estimating the variance that I didn't have time to discuss so much yesterday, and this is via replicates. So when we say replicates, we have more than one measurement per combination. That's the difference. So here we set up our design with A, B, say, and then A, B, and then we get Y replicate 1. So then this is -1, -1, 1, 1, -1, -1, -1, 1, -1, 1, 1, 1. And here we have some observations for the first trial. And then we try a second replicate because it makes it, the setup of this experiment makes it easy to get replicates. This is not always the case, but sometimes. So then we try again for exactly the same combination. We measure a second time. And now since we have 2 measurements for each combination, we can use the variability among those measurements for this one, for this one, for this one, for each combination to estimate the variability. So then we're not directly focusing on the sigma effect, but we're rather addressing this one. That's our focus because now we say that Y observation I is some combination of inputs, high and low, and then a regression term, and then epsilon I. And this epsilon I has variance sigma squared. And we estimate sigma squared directly from the variability among the replicates. And if we can get then sigma estimated through the usual s squared in some sense, then we can also use the connection between the sigma and the sigma effect to find this relation. So replicates is somewhat different, where we study the residual term directly. Okay, so here's how we get to do this. We take the sample variability, so remember this, for each combination of I, where we look at the measurement for this one. So this is then combination factor, combination I, and its replicate number J. And there might be something special for this factor combination or a combination one way or the other. So then we can use this as the mean for this factor combination. So the response should be the same because the covariate or X in this previous setup or the design matrix is the same. So the only thing that should vary is this residual noise term. And then we're estimating this from the sample variability within the same combination. And this could vary a bit between the different combinations. So that's why we average all of those in the end. Maybe sometimes for some combinations there are more variability, but then our assumptions say that it should be the same. It's the same sigma no matter what. So that means we just average it. And then this goes into a t distribution again, where now the v is changed. So this is based on the degrees of freedom in the S square calculation. And this would be relatively huge, 2k, because there are 2k terms here, and then we have r minus 1 for each component. So usually if this is large, a t distribution is relatively close to a Gaussian distribution. Okay, replicates. There are some questions about replicates here. Yeah, so if let's say you work in a lab and then it takes quite a long time to set up your configuration. So if you have designed things in the lab so that you're ready to do this experiment, say you set the temperature, you set the humidity or something in the lab room, and all the equipment is the right equipment is in high and low, then it might be so much effort for you to run an experiment many times. In some cases, it's not always like that. But then uh, lab experiment person, lab engineer one can run it once, and then he goes for lunch. And while he's eating lunch, lab engineer two also does the same experiment because it doesn't take so much time. And then you get two replicates for the same configuration. And then after lunch, you change your lab setup so that now you turn things on or off. Again, you repeat the experiment two times by the first engineer and then by the second engineer. And then you could, from these two, or maybe you get a third replicate if there are more people involved, or if you can just do it again the next day, say. So these are replicates. So statisticians love many fancy words. So there's a whole dictionary out there. So replicate means uh, many runs, but you have the same configuration, or many experiments under the same configuration. Okay. Yeah, and so this is nice in some settings. It's not so easy to do in other settings. So you see that from my example here. In some lab experiments, this would not be easy because it takes such a long time to run to get the actual uh, measurement here. So if it depends on the setting, and this is also something we want you to discuss in the project, in the second project, because you might do something where replicates are very easy to do, or you might do something where replicates are almost impossible, or it would take much time for you. So then you can discuss what your choice is there and why you made that choice. One way or another, you should estimate the variance, and you can either do it by replicates or you can do it by removing higher order terms. And then you get different distributions where you check your effects. Yeah, here was this example that is from the note that you could read when you have the time now for the second lecture. So there are two replicate runs then, and then we look at the difference. So this is one replicate one, and this is two, and then you look at their difference and take the sample, or from this you can extract the sample variability. And then we get 8, which is like our sigma estimate, and then the sigma effect estimate is 2, because in this setting there are 4 factors, so there's 8 measurements, and then this is normalized in the right manner. Yeah, so of course you would not go through this exercise in your project. So that's something we see in the when we go through these projects. Some of you like to do things by hand, and I really appreciate that myself. It's good to just have some control using pen and paper. But most of the time, it's easier to do these things on the computer. Just load the data or input the data and let the computer work. But pen and paper is good to do more like abstract things or understand things. I really understand that part. I do that too. Yeah, okay, so this lengths thing, what is that about? So length was a guy who thought that it could be possible to estimate the variability without having to remove interaction terms. Yeah, so how did we get this 8? Uh, 8 is the sample variability here, I think, and 8 is driven by this large difference that you have here in this column. Oh. So 8 is this difference. Oh, averaged over all this. So the average variability over these average sample variability here is 8. That's how we got 8. I think this is described in the note. It's the sample variance, just like you compute usually S squared without any kind of complicated um, regression terms in there. It's not exactly the average of the last column because there's a difference here. So here you would the sum of this one would be then the first one minus the mean, and then the second one minus the mean. And then you also know that this one average is yi1 plus yi2 half. So then you can split this into terms where things cancel. Yeah. So it might actually be the average of the last term. I need to write it out to see, but it's just going around these terms, linear combinations. Yeah, so Lent thought that instead of doing this, you can use the median. So this is based on, so this is, you can see appendix of this note. We'll look for this. So this is based on some properties of the median under Gaussian modeling assumptions. So the median is sometimes more robust or more sort of providing more insight than the mean. So it's more difficult to compute things with the median, but still you know some properties here, and he tries to use this, and then you sort the values and you cut it in some way to estimate this pseudo standard error that is used to find the significance level here. So it's a slightly different approach, which is not so important for us because it's sometimes drifting off quite a lot compared with using the actual data you get from replicates or using higher order terms. So I think we would prefer that. Okay, so then let's move on to sum of squares, because this is something we studied for regression analysis, and we also looked at this for analysis of variance. And recall that the total sum of squares, what is the total sum of squares? This is, in previous settings, it was the difference from the observations to the mean. And then this regression sum of squares is the difference from the fitted regression line to the mean. So how much is the regression changing compared with the mean? And then this error sum of squares is the variability in the data around our regression line. And we have seen that the factorial designs can be viewed as a regression analysis. So that means this y hat is basically a special kind of regression where the design matrix is filled with ones and minus ones. And this minus one and one structure means that for this 2 to the power k experiments, SSR has a very special form. And this goes back to orthogonality properties of mate and sort of more linear algebra properties, which we might not have to go into so much, but I want to show the main idea behind this and the result, because it's quite nice and it makes it easy to separate the variance components. So remember that this is the least squares estimate. And in our case, X has this particular form. And we saw that if this was right, what is then X transpose X inverse? Well, we saw this was diagonal because all these columns are orthogonal. So they are all columns are orthogonal. So because they are orthogonal, this matrix X transpose X becomes a diagonal matrix. So in this particular example, where we have 4 experiments, we get 1 over 4, 1 over 4, and so on, and 1 over 4, 0, 0, 0 on the off diagonal. More generally, we have n 2 to the power n k experiments. So then this one becomes 1 over n, 1 over n, 1 over n, and then 0 on the off diagonal, where n is 2 to the power of k. And since this is orthogonal, this sum of squared regression error becomes this nice sum where this factor here is also given from this matrix structure. So this is also minus 1, so this just becomes 2 to the power k, or n equal 2 to the power k. So we can then easily split the effects into one that has to do with the first factor and the second factor and so on. So here, remember that B1 is computed by the regression line where we take averages. So then we, in this case, would divide by 4. And since we divide by 4, this is half of this a hat where we divide by 2 only, because then we take average high and average low. And that's the same for the other ones here. So B2 would then be B hat divided by 2, and then it follows through like this. So this means that the SSR can be split because of the orthogonality into components of the different types of the different effects, main effects and interaction effects. So but why, how did I get here? This is still unclear. I just wrote up this formula, but there's some kind of math behind this. And the idea is based on orthogonality. So since we have, what is this y hat I here? Well, we can write this as x, I, and then b. And xi is just 1 and then something with plus minus 1, plus minus 1, etc., depending on whether this combination of I is high or low. So in any sense, this would be first that the first effect that we have is the mean, because this is the first element in this vector B, the mean value, and the next element are the main effects. So then we get plus minus a hat, or actually a hat half, and then plus minus b hat half, and so on. And in the SSR, we see that, okay, what's in here? It's the yi hat, so that's a fitted regression model, and then minus the mean. But the mean is always in here, so this just cancels. So what we get in the end are the main effects, and then summed out, squared. But the squares would only involve the terms that are a hat squared and then b hat squares. There are no cross terms. So cross terms disappear in this SSR expression because the columns of this X are orthogonal. And that's why we get something as simple as this, where we can take out the effect of A and take out the effect of B, and they just add up nicely. So it's easy to split the sum of squares into the various factors because of the orthogonality. And more formally, like in math, you might remember these hat matrices that I talked about. So then recall there was something called hat matrix. And this hat matrix was y hat, and then we said that this one was, well, x times b, and we know what b is. So then this is x, and then x transpose x inverse x transpose y. And now we saw that, okay, this part was just diagonal. So that's easy. It's just a constant times an identity matrix. And if we look at the sum of SSR in this setting, what is the SSR? Well, that can be written. So if we call this the hat matrix, then this one becomes the hat y minus some other transformation of the G matrix, and then transpose hat y minus G y. But since all columns are orthogonal, the mean would cancel, and you see that this splits out into a nice sum like this. So that's what happens mathematically. But it's not so important. It's more important to see here that this becomes a sum. So let me round off. Okay, yeah, this is also related to contrasts. So do you recall these contrasts that we wanted to test to see, say if one linear combination is equal to 0? So these linear combinations that we have here, they are contrasts. So what do we have here when we compute this B1? We have minus, plus, or some other combination of minus plus that always sums to 0. So these are contrasts. They're just like these contrasts. And for contrasts, we could also compute the sum of squares because it was a linear combination, and we could take the linear combination square to get the sum of squares. And then we could either use a t statistic on the contrast, or we could use a Fisher distribution where we had 1 degree of freedom for this one, and then we had other degrees of freedom for the denominator that estimated the variance term, the SSE divided properly, like properly. So these contrasts are again similar to what we have here in this sum. This can be written as a sum of orthogonal contrast, the SSR. So here's just one contrast. Yeah, let's show what happens again in this example with the catalyst. So then if we plug this into Minitab, we can easily get the out this plot, and then we see these. So this is then my SSW, where W is equal to the linear combination of A hat. And this would be the SSW, where W is the linear combination of B hat. And then it continues. And they are orthogonal. So they sum up in the SSR. And we see that here. So this one is 1100. And this one is 400, 600. So then we're nearly there already. There's a large variability in the A and the B, not so much in C and D, but then they combine, give the little extra to get 1100. Then we get the same for the interactions. They are also orthogonal with each other and with the first ones. So there we see that 580 is largely covered by this AB interaction. That explains a lot of the interaction terms. Very small for the other ones here. And then there's some left for the error here. So this is then SSE. And in the end, we get SST. So this is, if you do factorial analysis in Minitab, you get this for free. Okay, so next week we will continue on factorial experiments. Then we will discuss something called blocking, which is not very different from what we did in analysis of variance. We want to block things properly here to avoid special biases in the way we do experimentation. And what we cannot block, we randomize, just like in ANOVA or analysis of variance. We will also discuss something called fractional designs, where we say that, okay, 2 to the power k is very large. We can't afford that many experiments. So let's reduce the number of experiments to 2 to the power of k minus r, where r is maybe 1, maybe 2 or 3. And in this setting, we get something called confounding, which is yet another statistical term. Confounding means that you can't really separate some higher order interaction effect with a main effect. So then you might be in problems. You have to check things. Yeah, and finally, we will cover some response surface methods, which are very commonly used, and just briefly touch that. Yeah, and then do the project in the week after. Yeah, so finally, I'm sorry for the confusion here. I did post this in the wrong way, but hopefully you got something out of it, and you can now read the note, and then I'll post the recording of this one. So thank you. Have a good day.